Okay, we're ready to begin. Welcome to our Tuesday Tech Up Talk. I am on a quantum kick, and we're really pleased to have this talk today, which is going to be, you might think quantum light means that it's not going to be substance. There's a lot of substance here. So use the chat function. Feel free to ask your questions throughout. We have prepared questions, but we'll integrate them in as much as possible. We only have 44 minutes left, so we're going to kick this off. Welcome. So today I have a different professor. I have Nick Vamivakas. He is the Marie C. and Joseph C. Wilson Professor of Optical Physics, the Optics Institute at the University of Rochester. And if you haven't guessed, I am an alumna of University of Rochester, so I've been tapping into their expertise. So, Nick, let's begin with your research in quantum optics. As to me, it's such a niche within the optics and the
Mhm.
quantum spaces of 2026. So, will you share a brief version that summarizes your years of study that brought you to this point?
Yeah, first, I just want to thank you for giving me the opportunity to take part in this today, Kathy. And I also enjoy the title of Quantum Light. And I'm glad, kind of continuing that play on words, I'm glad you have Tech Up for Women taking a big quantum leap into quantum science and technology, because myself and many other people find it to be very important. Yeah, so my research for, I guess, now almost the last 25 years or so has really focused on the fundamentals of light matter interaction. That sounds a little bit complicated, but it's kind of, we're all so familiar with it. We, in some ways, take it for granted, right? We have incredible, most of us, detectors of light, our eyes. We are familiar with light sources, right? Light bulbs, the sunlight, and then all kinds of different tools to control light, whether it's eyeglasses, mirrors, sunglasses. And so kind of light and matter interacting with one another, happening all around us. Now, what really got me interested in kind of what made this connection into quantum optics and quantum photonics is to really understand the fundamentals of it. You kind of have to peel back all of the complexity and ask questions about what happens if you can have individual atoms, believe it or not, one atom being actuated by light and looking at the light that comes back from it. So to really make this whole research area go, we needed a technology that was developed a bit over 60 years ago, actually two technologies. We needed lasers, believe it or not. So light sources that had one color, very directional. All right, that was very important. And then we needed detectors of light that could detect very faint, feeble light sources, very weak light. So imagine in your kitchen or your dining room, that dimmer you have, you take that dim switch down, the room looks dark, but there still could be some light bleeding into your room, and we needed detectors that could see that light. Once we could do that, we learned very early that the type of light that could come back from these atoms was very different than laser beams or sunlight or candlelight or light bulbs. We could create beams of light that at a very particular instant of time had one photon and one photon only.
Hmm.
So we call these single photon states of light or quantum photon states of light. And then there is other light that we could create from the similar platform where now instead of having individual photons, we would have pairs of photons. And these photons are correlated or connected with one another in kind of ways that you wouldn't expect if all that you were familiar with was light bulbs and laser beams. And we call these entangled photon states of light. And so these two light states now are resources that are driving a wide array of different quantum technology, be it secure quantum communication or even quantum computing based on quantum states of light.
Wow. Okay. So, um, we know a lot because we've had a few quantum things, and so we even can follow pretty much what you're talking about beyond just the lasering and all these things. So, and my next question is about the study of light and quantum optics, introduction to the photon.
Mhm.
Um, where you are now. 60 years later.
Mhm.
Um, what is our understanding of light relative to quantum?
Yeah, so I mean, the whole research domain of quantum optics really kicked off in the 1970s, actually at the University of Rochester in our physics department here. And the first experiments were done that kind of conclusively proved that light, as we understand it, is made up of constituent particles, and we've used the word a few times, but is comprised of individual photons. And the way that this demonstration played out was, again, I had something like this individual atom. I shined a laser beam onto it, and then I looked off in a different direction, and I had a piece of glass, and the glass would send light either to the left or let it pass straight through. And one of the fundamental properties of photons, and this hasn't changed in the last 50 years, is that they can only be in one place at a given time. And so if I can create a beam of light that has a photon at a given instant of time, and I send it to one of these glass plates that sends light off to the left and that light passes through, and these are those detectors I was telling you about, and I just look at the clicks on the detectors. All right. And as I look at the clicks and I record long streams of data, what I discover is whenever I have a click on detector one, I never have a click on detector two. All right. And it seems kind of obvious as I tell it to you now, but back 50 years ago, it wasn't so obvious. And the beam of light that was coming from the atom that this was going to be the case. Because if I were to put a laser beam or a light bulb or a candle into this similar thing, never would I have a stream of clicks. Where on detector one, I was guaranteed never to have one on detector two. Right. So there was never any of these kind of false positive situations. Now, that hasn't really changed the kind of fundamentals of the photonic nature of light. What has started to change and even accelerate more recently is creating systems or engineering systems around light sources that can deliver beams of photons that have very high, meaning are very bright, meaning that I don't have to wait a very long time to get a photon. They come pretty regularly. I can send them off in directions that I want them to go. They have the color that I want. They have other kind of desirable properties that are inherited from the engineered system we put around them.
So I'm going to ask a really
Yeah,
basic question here because I know nothing, but you can actually see these single photons in the light spectrum.
that's right. So actually, our eyes, if you get into a very dark room,
Go
and
back to that one.
yeah, if you go back to a very dark room, in fact, our eyes are sensitive enough to register the detection of these individual photons in these streams that I'm talking about. So you can the photon has a direction, it has a color associated with it. So if I use my eye, I mean, this experiment hasn't quite been done exactly like this, but you could imagine seeing the color of these individual clicks if you were able to sort of repeat enough times. Yeah.
Because one thing I've learned about quantum is that it's it's um it's such a difficult source. It's a difficult study because you're believing that you can see things you can't really see,
Hmm.
right?
Yeah, yeah. So I mean, I
But with
think
the but with the quantum light, you can actually see it.
that's right. You can see, certainly you can see the quantum light, and in many ways it was built on, again, uh, initially that,
Repeat it again.
yeah, no, it was of course built on studying things that were far removed from our everyday experience. I think that's
Right.
often the case, right? And now as some of the fundamental properties of both the single photons that we've been talking about as well as entangled photons have matured, the devices we're engineering around them are creating now these cool quantum states of light that, as you said, could be observable to even the naked human eye.
So in quantum physics with the one zeros that are you have to just like believe. This you can actually
Can you can see it, but the some of the interesting parts come from
what you
how how we measure it and
What you
proper.
can't see.
Yeah, yeah, that's right. Right.
I love science.
Yeah.
I sent one of the quantum prior things to a friend, and she goes, "This is sort of like believing in God," which was an interesting topic. But anyways, the research you're working on, when we had an initial conversation, it is so fascinating, the research you're doing right now. And
Uh-huh.
you have some really practical examples of them. Do you want to just talk about a little bit about the applications and what you personally are
So
working on?
yeah, so right now we have a pretty big activity in Rochester that's a partnership between my lab at the University of Rochester and then Professor Stefan Prebble, who's at Rochester Institute of Technology. So they're about 10 kilometers down the road from us. And what we are building here in Rochester, we call RockNet, is an ROQNET. And we've been creating a quantum networking test bed that consists of optical fibers that connect my lab with Stefan's lab. And what we are trying to do, and we have been doing, is sharing initially these single photon states of light through this quantum network, and demonstrating that we are able to do this at communication rates that are potentially usable for a kind of future application. We're also studying how we can use these states to communicate securely. So one of the big applications, early applications, and say some of the probably first actual translation to technology demonstrations were in the space of quantum secure communication using quantum light. In the more recent experiment that we're now working on is to create shared quantum entanglement between our two labs, again, using entangled states of photons as the mediator to share this quantum entanglement. And so entanglement is another kind of quintessential feature of quantum mechanics that shows up quite a bit in popular science because of its somewhat exotic and counterintuitive properties.
I know we learned about that so far, entanglement. It's
Okay, good.
a great phrase. Um, so communications is and secure communications is one of the early applications that you're actually testing.
Yep, that's right.
And it's not just with within your lab testing, it's a between
Yep.
another lab and you.
Between another, yeah. So I think that that's one of the maybe so quantum optics and even more broadly quantum information science within the last 10 to 15 years has been moving from, I would say, kind of the first, well, sort of understanding some of the fundamental science and then tabletop proof of principle demonstrations in individual researchers' labs to now really scaling up and trying to translate these ideas into practice. And so there's as much kind of foundational quantum science happening as engineering around quantum systems to make some of these applications a reality. And so these are both equally important, but their challenges are very different. And so, to your point, we are not just doing these experiments, which we have done in my lab before, and Stefan's done in his lab. Now we're seeing how can we do these across the city of Rochester and deal with all of the realities of trying to use quantum states of light to communicate securely as well as share entanglement between distant locations within the city.
We have a question about the military using quantum light communications. I don't think you're at that point yet where it's application. I mean, this is an early, this with Rochester Institute of Technology, this is an early, um,
Yeah, this is
very early.
we're on the early stages of doing these kinds of demonstrations, but other countries in the world certainly have done demonstrations or are using quantum cryptography, it's called, to actually securely communicate. I've heard that China, in fact, is doing this. It's been used, I think, in Europe between banks for secure communication. So it is something that has been adopted, not widespread yet, but it has been adopted and uh, has been kind of deployed so it's robust enough to deal with all of the realities of being out there in the world and not just in a research laboratory.
Thank you for the question, Candace. We're still researching. Marie has a basic question that used the word about entangled photons.
Yeah.
Um, how do you create entangled photons?
Yeah, so there's a number of different ways. The way that is most predominantly used in the community is part of what we refer to in optics as nonlinear optics. And basically what that's a fancy word for saying is that if we put light or laser light of one color onto a material, a crystal, and look at what comes out the other side, different colors than what we put in come out the other side. And so there's a whole range of color distributions you can get on the output side, depending on what color you put on the input side. And so, in fact, if you do this just right, you can send in, uh, you can send in light of one color, and then what comes out the other side are beams now, and these beams of light that can have the same or different colors also exhibit this property of quantum entanglement. And so that can be done on a tabletop in a laboratory. There's ways to scale this down and do it on integrated photonic chips. I saw there was a question in the chat about that, about quantum photonics on chips. And so again, this comes in, the sort of foundational stuff was done on optical tables with crystals that you shine light on one color and can get these entangled photon pairs out the other side. And now we're trying to come up with ways to do these, make these same kind of light sources, not on a big optical table, but down on a small photonic chip that you can take out there into the field.
Interesting. Most everybody knows I live in New York City, and maybe 2 or 3 years ago, up at Central Park, they had an art exhibit. They have a big place right there at, where you enter Central Park by the horses. And the art was where you're one side of a crystal or a quartz piece, and on the other side, you could see the light splitting off.
Yeah.
It was a really fun exhibit. So artists are also using this.
Yeah, well, definitely yeah, effects with light are typically cool because they're very visual, right? And then they can create some really lasting impression.
Yeah, I love it. Um, we are getting some more questions, which is great. I see there's one that just came in about how embedded is quantum in the university curriculum from
Yeah,
Carol.
yeah, that's a great question. And I would say every day we are having more and more infusion into the curriculum. It's kind of interesting. So at Rochester, like I said, the first experiments in quantum optics were done here in the 1970s. And because of that, at least in the field of quantum photonics and quantum optics, we are very ahead of, we have been ahead of other universities. We've had a very strong and robust curriculum in quantum optics and in quantum science. I would say now, again, with this last 15 years, there being this really renewed tension on translating things from the laboratory into practice has also been happening in parallel to a recognition that quantum science and quantum engineering needs to have a bigger place in curriculums. And so that has been steadily happening to the point now where universities are offering undergraduate concentrations, graduate degrees, both at the master's level and the PhD level in quantum science, quantum technology, and quantum engineering, depending on where you look.
Great. Let's see, where do we go next? What else? Are there other applications coming to market?
I mean, I think there is a big race, maybe is one way to say it, to see who can come up with the first quantum computer. Probably, if you said you had some other colleagues from Rochester on, they were talking about probably in part quantum computing and there are approaches that build on the kind of expertise and know-how we've kind of created as we've built up the semiconductor fabrication industry and silicon integrated circuitry. And so there are approaches to doing quantum computing based on that, but there are other approaches that are based on using laser light and atoms and ions. And then there are other approaches that are on integrated photonic chips using just light itself. And so right now there really is a lot of interest, attention, and energy being put in to create a quantum computer. And I do think that that's probably one of the next, hopefully, big, breakthroughs we have in this area.
Right. We have had that, and we 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 have other firms that are sponsors of Tech Up who are working hard on being the first out there with those quantum computers. So,
Yeah.
um, big believers in that. I'll go back to Kansas's question about blue light and blue light blockers. Um,
Okay. So what was the question? I'm sorry, I didn't catch that one.
yeah, it was early on,
Uh,
and
oh,
the does the eye does
so
the eye
uh,
actually?
yeah, the eye will see blue light definitely. And the blocking glasses, the idea behind them is to just essentially put a filter into the lens of the glasses that keeps the blue light from passing through and then lets the other colors um, make it into your eye. It's a it it uh, it operates on a different physical principle, but has the same idea as sunglasses. And there's a reason I'm saying this. And so you can buy polarized sunglasses. I'm sure people have heard of those. And so light has a internal property that we call polarization, and it's an orientation. And common light orientations would be like up, down, and left, right. And so if you're looking out at like the water sitting on the beach and the sunlight comes up off the water, the orientation of that light acquires the orientation of the scene that you're looking at. And so polarized sunglasses have a special filter that now doesn't deal with the color, it deals with the orientation that will block out the light that comes towards your eye that's oriented along the horizon you're looking at. Now, you also know sometimes that you'll buy polarized sunglasses and they don't seem to really do anything. And so first buyer's tip one, if you are somewhere in polarized sunglasses or advertised, what you need to do is take two pairs, look up at a light and rotate one at 90 degrees to the other one. And things should get black through that lens. And those sunglasses are polarized. So the reason I'm sharing that is in Candace's question, said, do those blocking glasses actually work? I would say I'm not exactly sure. We would need to, just like not every polarized sunglass is made the same way. I suspect not every blue blocking eyeglass is also operating as advertised.
Okay, you heard it here on Tech Up for Women, a way to buy your sunglasses. Like,
Polarized sunglasses. Take two and
don't just
rotate.
buy them without.
Yep, don't do that test first, so you know you're actually getting polarized sunglasses.
Um, okay, we're getting a lot of questions today, so I'm glad we went for the whole 45 minutes. Um, let's see. Meg
Oh,
is asking quantum optics advances new communication simulation. Do you imagine spatial or immersive interfaces becoming useful tools?
that is,
Or
yeah. So I'm seeing this question now. Uh,
we don't usually have this many questions that we have to sort through. This is exciting.
I'm kind of delaying trying to think about what I want to answer
The
now. I'm not.
answer.
This is a good question and one I haven't.
Well, I
I
know Meg. Meg is also at the University of
I
Rochester.
I also know Megan. That's why I know when this question has come. I
So
can
you're being really careful.
yeah, but I don't. To be honest, I don't have a good answer to that just because I haven't thought about it very much. My gut reaction from other areas of research that I'm involved in is that the answer will be yes. It's just coming up with creative ways on how to do this. But to this point, I haven't really thought too hard about it. Sorry, Meg.
We'll have to have both of you on sometime. Um, Gudrun he said we must have skipped his. We did. We skipped his question about semiconductor. Um, it was
Oh, okay.
very early on about um, semiconductors and research in that regard.
Yeah, I mean, there are a lot. I mean, in the quantum space, there are companies like Quantum, Xanadu, Quandela that are trying to do integrated quantum photonics. Also, other bigger companies in the past have, at least at various points in time, like Intel, IBM, have had big efforts in integrated photonics also, if that is getting to what the question was asking.
Yes, here it goes. Photonics is being applied in the semiconductor industry. IR Labs is an example. Which companies are most advanced in the field of optics?
Yeah, I think that sounds right, what we said.
Right. He also then asked the second question about the quantum computing. Um,
Do you think? Yeah. About the company in France, is that the one?
Pasquale,
Yeah.
Pasqual.
Yeah. I don't want to get into the speculating on who it's also hard to know because the many of the companies, of course, share some of the successes they have, but they also have lots of challenges that aren't always so obvious from those of us looking from the outside and trying to figure out exactly what they're doing.
Yeah. Okay. Um, where should we go next? We have um, quantum computer. Yeah. So you're not going to venture an opinion, if they'll succeed or
Yeah.
not because you're on the outside. And
Yeah. Yeah. It's hard to say that.
okay, um, patents. Are there a lot of patents in this field? Do you have any patents? I didn't ask you that.
Yeah, in this field, actually, in this area, I don't have any. I at the moment don't have any patents. And some research kind of connected into what Meg Moody, who we were just talking with, does. I do have some patents in that area, but yes, there are definitely the University of Rochester has IP in quantum information and quantum computing, and of course, there's lots of other folks that have intellectual property in this area also.
What's amazing for me is because I am over the age of
Yeah.
50, 60. I mean, I graduated from Rochester in 70s, so 74. So we know my age. What's amazing to me is in my very brief lifetime, all this has come to be. I mean, it's like I have a t-shirt about ones and zeros and when
Yeah.
we first I took programming in high school in the 60s. All this has come to be
Yeah,
in
it's
my very brief lifetime.
no, it's amazing. I my the so some I give a summer school course at the Institute of Optics as part of an industrial associates program we have. And at various points, I've given one on quantum science and technology. And to your point, one of my favorite slides are pictures to show and kind of leading into whether any of this is real and will we get to quantum communication and quantum computing, because a lot of the instruments we need to use now kind of remind people of the old computers that filled rooms and don't just sit on our desktops anymore. But if you look, it blows my mind still is that if you look at the picture of the first transistor, one, it's like the size of a quarter. So I don't have that picture here. And now if you look at the size of the integer, like the microprocessors that sit in our computers that have billions and billions of transistors are now the size of that quarter. And that's just like a remarkable feat of kind of engineering and design and all of the things that go in the last, what, 70 years to get from something one is the size of a quarter and now billions of those things fit in the same size. I mean, it's just numbers
Yeah,
is hard to wrap your head around.
I know. Which one of the questions here now, because this is getting to be a group conversation,
Yeah.
is AI and what's is quantum gonna really burst AI where it makes a lot of things more feasible.
Yeah, I mean, so from one perspective on that is that it will give us more powerful computing resources. So it can potentially help with, I would guess, I'm not certainly, I want to like I'm not an expert in sort of artificial intelligence in any means. So take that, but but in some of the processes to create the models and the training, I would imagine that there would be opportunities there to do things more efficiently. Now, whether it gives breakthroughs that lets us go from the types of models we have now to have more powerful models that can do things that they can't currently do, I'm not so sure about that. My understanding right now is a lot of the advances in artificial intelligence is not coming from kind of chewing on ever greater amounts of training data, which takes a lot of compute and a lot of energy, but sort of fine-tuning the model after it's been put together so that it can become sort of very good at a specific task, but maybe not be as general purpose as one would have hoped to get out of the models on the front end. So,
Yeah, I've read some articles about how AI is going to hit a wall.
right.
And if quantum doesn't continue its research and have quantum computers out there, that wall is
Mhm.
going to be a solid wall for
So,
AI moving forward.
mhm.
It was
Yeah.
in Forbes. I think maybe I sent you that article
Yeah,
in
I think
Forbes.
yeah.
That was an interesting one. Um, so I don't know,
So
Carol has the question about any update on early stage cancer and biomarker detection.
yeah, I'm not sure. So this might be completely disconnected from the question, but there is,
That's all right. I don't understand the question connected to this topic, so maybe
yeah,
you
so
could.
so there are, so we've talked about communication and we've talked about computing. There is also a whole area of quantum enhanced sensing and using kind of properties of light or actually properties of materials to sense things in ways that we would otherwise not be able to do. And so actually one of the experiments we do in my group here is not as much related to light, but we work with diamond nanocrystals, so really, really tiny, like to orient if I took out my slowly disappearing hair, I don't really want to do that. But if I pulled one piece out, the diameter of my hair on average human hair is about 100 micrometers. And so if you go down about 1,000 times smaller than that, just to orient everyone, that's 100 nanometers. So like just and so that we can get diamond nanocrystals that are even like 10 times smaller than that. So 10 nanometers, and they have within them a defect actually. So defects are what give diamond the color that people don't like if you actually buy a diamond that you might put on like a necklace or your finger. But those defects also have properties that can be used to learn about the environment. And so we have a project actually in collaboration with someone in the medical center to do biomarker detection using these
Hmm,
diamond nanocrystals, and the whole protocol to measure essentially the properties of the biomaterial that we're looking at is based on quantum mechanics and quantum information. It's not connected into cancer. I'm not sure if that's what Carol had in mind with her question, but there are definitely opportunities in medicine, not only, I guess, to do computing for drug discovery, quantum computing for drug discovery, but also quantum sensors to let us actually come up with diagnostic tools that outperform what we currently have access to.
interesting. So you see the connection um, more than I do.
Yeah,
That's because you know everything about this that I know little, so little. Every time I learn more, I
yeah.
realize I know less than I even
Well,
thought I knew.
I think that's the case for everybody. There's a,
Um, okay, I think maybe we've exhausted the questions. If I skipped somebody, send me a note here because they did come in there rapidly. Is there anything I missed that you're seeing there, Nick?
I don't see as I'm kind of scrolling through. I think we got a lot.
And let me see if we had any other questions. Well, the one thing that I saw Marie asked about was a curriculum. we obviously have a group of individuals on who are very fascinated by the topic. And what I told you, the people who registered for this are not our, there are a few of our regulars, but
Yep.
a lot of people. Seems to be a void.
Mhm.
And so if somebody wants to get more educated about quantum, where
Mhm.
do they go? They go take your summer course or
Yeah, they could take our summer course. Of course, there's lots of content you'd find on places like right YouTube and other places on the internet. But like I said, there are now starting to be, it depends on where you are, also kind of in your academic journey. But graduate programs, master's programs, PhD programs, master's certificates in quantum science and engineering. And so it depends a little bit on what someone's interested in, and that would certainly guide the kind of choices that are being made. And then what I mean by that is there's a material science bent that could be there if you're so inclined to material science. There's of course the optics and photonics that I'm talking to you about. There's the semiconductor device access to it. It's and all of these are components of a curriculum that one might study with different concentrations in those areas for quantum engineering and quantum science.
let me say, most of our Tech Up for Women audience are
Yeah.
individuals like myself that
Mhm.
want to learn more.
Yeah.
I don't think we may have a few on
Yeah.
today who are in the academic world, but um, like right now, you can get certificates in AI. You
Yep.
can't just casually get a certificate in quantum.
Yeah, that's true. So the definitely our summer course series is a online remote activity. So when we do that, that is one way to learn something more about quantum that has a bit more of an optics bent to it, of course. Uh, yeah.
Carol has another question about discrete credentials for security and communication courses.
Yeah, I think that's maybe kind of touching on what we were just talking about is
Hmm.
I think it's been a little bit of a chicken and egg problem, to be honest, too, as we've talked for some time, not even, I mean, we've talked about, meaning us at the University of Rochester is like, what is the right um, credential curriculum um, degree that we want to offer and wanting to make sure there are people who are interested in it. And also that if people pass through some offering we have, there's value on the other side of it for them. And so, like in discussing a master's program, right? Wouldn't just make a master's program in quantum engineering to have a master's program in quantum engineering or quantum science. We want to make sure that there are opportunities on the other side of that program for people to go out there and find work. And so, I think that the last handful of years have shown that the case is that there is places that are looking for folks who have these credentials or understanding. So we haven't said maybe we should dial back and instead of thinking of masters, think about a one or two course certificate or some other kind of credentialing program that is maybe a bigger tent, but more accessible to people and not as big a time commitment as something like a degree program that we offer at the university.
I think we've exhausted June's question about other potential future uses, but she does ask the question about timeframes. Like we've talked about quantum as 2030,
Yeah.
quantum physics, but any
Yeah.
timeframes as some of these applications get developed?
Yeah, I mean, so I think the secure communication or quantum secure communication already is, if you like, has matured to a degree that it has been deployed. I think we haven't talked again a lot about the quantum sensing, although we sort of digressed into that. There, I think also there are products available, and I think we'll be having bigger kind of impact in industry in the 2 to 5 year time frame, and then I think optimistically, folks hope 5 to 10 years for a quantum computer. I was just reading something the other day that was kind of sharing that enthusiasm and that might happening. But the other side is I've been doing research kind of broadly in this area for 25 years, and I've always been hearing about another 5 to 10 years, and the quantum computer will be there. So I sometimes take those aspirations or those projections with a little bit of a grain of salt.
You have more of a bird's eye view on it than
Yeah.
I do in terms of what's happening. And just one last from Candace about red light therapy. Exists any other therapies? I don't know what red light therapy is.
Yeah,
Do you?
I can guess what it is, meaning like you shine light onto a person that helps do, or, but I'm not exactly sure.
Okay,
So I don't
Candace,
know.
we'll get back to you on a future tech up about this. But this says, oh, used to be in spas and health clubs.
Yeah, so must be something to promote skin health. I don't know. I don't know the mechanisms of it. So
You
yeah,
know, I was at the Consumer Electronics Show and I did try to go to all the quantum things I could go to.
okay.
And I did find some companies, but they're very, I mean, there's 4,100 exhibitors at the
That's
Consumer
wild.
Electronics Show. I saw two or three on quantum out of that 4,100. So we're at the cutting edge here. And this has really been, I love the questions. It's
Yeah, this.
hard. Sorry, I couldn't keep up with them all.
No, to be honest, I was worried on the front of this I was going to have to talk a lot, and not. It's been great to have so many questions coming in. It makes it. I can't believe the time has gone so fast.
I know because that was so action oriented. But Nick, do you have any last words in our last minute or two to add that we didn't get to? I was
Yeah,
looking at our list.
I felt like we hit everything you had put on the list. No, just thank you for having me. Like I just said, the 45 minutes went by in a snap. It went really quick. This was great. It's always nice to have questions and discussion instead of just talking. That makes everything more enjoyable. So thank you for having me. I really enjoyed doing this.
And we might have you back before 2030,
Okay.
2035, give or take 5 years.
That's right.
Um, I want to thank Nick for being with us. I also want to thank each of you for joining us and for being so active on the questions and the comments. And it was almost like a separate conversation. We did launch January our subscription service. So go to our website for techupventures.com and sign up for that, where we will have more in-depth conversations. This will be up tomorrow on our Tech Up for Women website. So we're so glad. And again, Nick, thank you. And I'm sure I'll talk to you before 2030 or
I'll
35.
see you before then. Thank you, Kathy.
Thank you. Thank you for being here. Have a good one.
Bye.